Second tutorial for this particular topic, and in this case we're going to look at problems like the molar solubility of lead iodide is found to be 0.765 grams per litre. Calculate the solubility. And the thing you need to know here is that lead iodide is of the form AB2, and so it's going to break up into more than 1 mole of ions. So as in the previous case, the first step to do is to write step 1. Step 1 is to write the equilibrium expression. So in this case it's going to be the dissolving of lead iodide. So PbI2 in the solid form is going to dissolve to form lead and iodide ions, but there's going to be a 2-to-1 relationship. So in this particular case we're going to get Pb 2 plus ions, 1 mole. So for every mole of lead iodide we're going to get 1 mole of lead ions, but we're going to get 2 moles of iodide ions. So in this case, if we look at this, for X moles of lead iodide, we're going to get X moles of lead, but we're going to get 2 moles of iodide ions, and we have to keep this in account. Step 2 is to write the solubility product expression for this equation. So step 2, write the Ks expression for this. So we'll do that right now. Ks is going to be equal to the concentration of the lead at equilibrium. And remember, you only put in the equilibrium values. And here we're going to put in the iodide. It's not, I'm going to take the 2 away from there. And remember, it's raised to the power of 2. because there's 2 moles of that, the coefficient is 2, we must raise the concentration of this to the power of 2. So once we've got step 2 done, we now have to calculate what the equilibrium concentration of this substance is. We're now going to go to step 3. Which is going to be calculating the equilibrium, the equilibrium concentrations. And for us here, it really is just a matter of taking the grams per liter and converting that to moles per liter first. So we're going to use N equals mass in grams over molar mass in grams per mole, and in this case it's going to equal 0.765 grams divided by the molar mass of lead iodide, and I've already got that calculated here. It's 461 grams per mole. So I'm going to put 461 grams per mole, and I'm going to do the calculation. It's going to be a very small concentration, so 0.765 divided by 461 equals 1.66 times 10 to the negative 3. So 1.66 times 10 to the negative 3 moles. Then I'm going to convert that to concentration. So C equals, and that's just going to be straightforward because again it was per liter. So this is just going to be 1.66 times 10 to the negative 3 moles over 1 liter, and so its concentration is simply 1.66 times 10 to the negative 3 moles liters to the negative 1. Once we've got that calculated, we can now substitute into our equilibrium expression the values to calculate the Ks. So we know what the concentration is. Now we just need to substitute these values in. So this is simply going to equal Now the concentration of the lead ions is exactly the same as the concentration of the solid that dissolved, so it's 1.66. But the concentration of the iodide is twice that. So we have to multiply that by 2 first and put that in. So that's going to be 3.32 times 10 to the negative 3 moles per liter. And don't forget, we've got to square this. So we've also got to square that. So we've got to multiply this by 2 for the iodide, because for every mole of lead iodide that breaks down, we're going to get 2 moles of iodide. And then we've got to square it. So the final step in our calculation here is now to use this information to calculate. So this would be the final step. Would be to calculate the KSP. So KS is going to equal 1. Let's square the 3.32 first, and then multiply that by 1.66 times 10 to the negative 3, and so you get 1.83 times 10 to the negative 8. And that's therefore the solubility product of lead iodide. The next problem is the molar solubility of silver dichromate is given as this. Calculate the Ks for it, or the solubility product. So let's do this a little bit more quickly. We'll try and do all the steps just following on from each other. So the first step is to, so step 1 is to write the equilibrium expression. So when silver dichromate dissolves, then it's going to So we're going to get 2 moles of silver ions this time. So for every mole of silver dichromate that breaks down, we're going to get 2 moles of silver ions and 1 mole of dichromate ion. Step 2 is going to be just writing the Ks expression. So in this case, it's just going to be Ks equals the concentration of the silver ion squared. Remember again, because there's a coefficient of 2 there, you have to square that. And then it's going to be times the concentration of the dichromate ion. So now we have to find what the concentration of each of these are and substitute it in. So let's go and do that. This is easy because we're already given the fact that the concentration of the silver chromate solid that dissolved was 8.66 times 10 to the negative 5 moles per liter. So in fact the concentration of the silver ions will be twice that, or equal 2 times 8.66 times 10 to the negative 5 moles per liter, which will be equal to 1.732 times 10 to the negative 4. So that would be 1.73 times 10 to the negative 4 mole liter to the negative 1. And the concentration of the dichromate ion is just going to be the same as the silver dichromate, so that's just going to equal 8.66 times 10 to the negative 5 moles per liter. And we put those values in to the equation and do our math. So let's go ahead and do that. So here's the KSP. Let's put that in. So this is now step 4. that value in for the silver, so the KS and we're going to square it. So what we've got here is KS equals concentration of the silver squared times the concentration of the dichromate we do the math and compute. So step 5 is to compute the answer, which is going to be .60. So the KS is going to equal 2.60 times 10 to the negative 12. So there we have the two types of calculations that you would have to be able to do at this level.